we can make a start. Brilliant, thanks so much. Okay, so welcome everyone to the fifth webinar in the series of the ePrime webinars. I'm Caroline Champney and I'm the publisher of the new open access journal ePrime here at Elsevier. Today, I and Karanesh Kant, who's one of our early career editorial board members, we're excited to welcome you to the webinar series. So Elsevier's ePrime was launched at the end of 2021. It's a new open access fast turnaround journal in electrical engineering, electronics and energy, launched to help increase the impact of your research across disciplines. Today, our webinar speaker is Professor Yongheng Yang from Zhejiang University in Hangzhou in China. We're going to present the power electronics technology for grid-connected wind and solar power PV systems. But before I go ahead and introduce Professor Yang, I just wanted to mention a couple of housekeeping points. So everyone will be muted throughout the webinar. And we ask you to go ahead and ask your questions in the chat as we go through, as Professor Yang goes through the presentation. And wanted to mention that at the end, if you did want to ask a question, then just raise your hand and we'll unmute you. Okay, so I'm just going to go ahead and introduce Professor Yongheng Yang. So Professor Yang received a PhD degree from the Department of Energy Technology at Aalborg University in Denmark in 2014. And he joined Zhejiang University as a ZJU 100 professor in December 2020. Prior to that, he was a professor, an associate professor at Aalborg University. So Professor Yang's research is focused on the control and grid integration of solar photovoltaic power conversion and systems and the reliability of power electronic systems. He was the recipient of the 2021 IEEE Richard M. Bass Outstanding Young Power Electronics Engineer Award, and also the 2022 IEEJ, the ICO Takahashi Power Electronics Award. Professor Yang was named on the list of highly cited Chinese researchers by Elsevier in 2022, and he now serves as a vice chair of the IEEE Power Electronics Society Technical Committee on Sustainable Energy Systems. He was also the chair of the Denmark section of the same. Professor Yang serves as a senior editor for Elsevier's journal for ePrime, and he's associate editor also for several IEEE transactions journals. So I'd like to hand over to you now, Professor Yang, and say a special thank you for joining us at this hour because it's late for you there in China. So please go ahead and welcome. Thank you so much.
Thank you, Caroline, for the very kind introduction, and good evening, good morning, or good afternoon, depends on where you are based now. My name is Yongheng Yang, as introduced by Caroline, and I'm now working at Zhejiang University. And today I'm very glad and honored to present some of our studies related to power electronics and control technologies for renewable power generations. Yeah. About the presentation, and first I will walk through with you all what is the current status of renewable power development. And then we will focus on the development of power electronics with a brief history review of power electronics. Then our focus will be put on the power electronics converters for wind and solar photovoltaic systems, because those are the two major renewable energy power generation across the globe. Then I will present the control techniques more specifically related to the some selective control technologies for power converters, because for different applications, the control targets, the control objectives are different. So we selected some typical control applications in power electronics based wind and PV systems. Then at the end, I'm going to summarize today's presentations. And of course, if you have any questions, I will be happy to answer and discuss with you. So as we all know, the global energy consumption is still increasing at a fast pace. As you can see on the right side of this slide, the figure shows compares the global direct primary energy consumption in the past two centuries. As you can see, around the 18th centuries, the primary energy resources is traditional biomass, but by the end of 2019, we can see the traditional biomass has been significantly reduced in the past two centuries, and those traditional energy resources are replaced by renewables as well as other advanced technologies, for example, nuclear or other power generation technologies. We see that in the past, it is a few fossil dominant energy consumption structure, but today it is more renewable based, and renewable is still increasing because seen from the global perspective, we see that the global nations, all the nations are trying to bring the temperature increase down, the 2 degrees C or 1.5 degrees C issues on the Paris Agreement. But in China, the government is also use the carbon emissions from power generation systems. We have this carbon neutrality strategy across the nation. So seen from the global perspective and also the national perspective, we will see more energy consumption that is met by renewable power generation. So when we look at the development of global renewable energy, we see that there is a significant increase in the past 2 decades. For example, for the major renewable energy installations in the past two decades, of course, the hydropower is the #1 renewable energy, and then followed by wind and solar energy. And among those major renewable energy sources, there are also bioenergy resource, geothermal resource, and the marine energy resources across the globe. But by the end of 2020, actually, the summation of wind and solar has exceeds the total installation of hydropower. And we will see the increase of wind and solar, and furthermore in the near future, because hydropower is geographical dependent. You have to install in specific areas or regions to get this power. Compared to wind and solar, those are less geographical dependent. And then furthermore, when we look at the renewable and the non-renewable annual additions in the past two decades, we also see that the non-renewables installations has been significantly reduced, and instead the renewables installations has been significantly increased. And by the end of 2021, the annual installation of renewables is 4 times of that of the non-renewables, and we will still see this big gap between the renewables and the non-renewables, and that is then in the future more renewables will be installed in the grid, and more non-renewable power generation will be phased out to tackle the environmental crisis. Yeah, and when we look at the power generation from renewables, what is the key? The key actually is the power electronics. Power electronics is the key components in the renewable power generations. For example, from wind, from solar, from nuclear, and even from hydro. And there are quite a lot of power electronics converters used in such applications. Here in this slide, we just briefly shows how renewables and other power generation systems are connected to the power grid and through the power electronics converters. And the power electronics today are seen in every aspect of the energy generation, transmission, distribution, conversion, and the utilizations. And we will soon see a power grid that is highly penetrated with power electronics. And in that case, we have quite a lot of challenging issues to face with and to address in order to secure the power supplies to have a reliable and a stable power system. And in terms of the installation of wind and solar PV, this has been also increasing exponentially in the past 2 decades, especially for PV systems. Actually, this has been increased in the past 10 years significantly compared to the wind increase. The wind power that is gradually increased, but for PV that has an exponential increase in the past 10 years. And some numbers, by 2021, approximately the total global installed wind is around 800 gigawatts, and for solar, that's around 850 gigawatts. And in the single year of 2021, wind and PV has been installed almost about 100 gigawatts respectively. And as I mentioned in previous slide, since 2020, wind and PV total capacity has exceeded the total capacity of hydropower. We will see more difference, more PV and wind compared to hydro in the near future. And another interesting point is the unit capacity is getting higher, especially for wind turbines. Today on the market, there are wind turbines, and a single wind turbine, the total capacity is around 15 megawatts. That's significantly huge wind turbine compared to the wind turbines in the past 2 decades. So this is a significant increasing. And for example, as I mentioned, for wind power systems, and because of the use of more power electronics, the power processing capability is increasing. Then we see much larger wind turbines, and this basically shows how the power electronics has been used in wind power generations along with its history. And in around 40 to 50 years ago, power electronics were barely used in wind turbines, and gradually they were partially used as, for example, soft starters in wind turbine systems. And to today's wind turbines, that's full scale power converters, because they enable the wind turbine generator systems to be more active, to process more power with high efficiency and high reliability. And with more power electronics in the systems, we will see a more larger scale adoption of wind and solar PV. And this, of course, is driven by the technological innovation, including power electronics as well. And this increase further reduces the total cost, the levelized cost of renewable energy. Then the renewable energy is becoming much competitive compared to the traditional energies. That's also one of the reasons why we will see more renewable compared to the other energy resources. But of course, this is also a task with global efforts and global policies, as I presented in previous slides. But anyway, in the future, we will see much more power electronics or electronics-based power systems. And that was about the development of renewable energy across the globe, and what is the major role of power electronics in such energy utilization or conversion, but how the power electronics was developed. This slide basically gives the history of power electronics, as well as the development of power semiconductor devices. And back to the 1950s, During that phase, people were exploring power switches or switches as nonlinear devices to control the energy or to convert to condense the energy. But entering into the late 1980s, then the focus has been changed from the exploration of switching devices to the circuit topologies, control modeling methods, and we focus on the performance improvement of such power conversion systems or energy conversion systems. And when we entered into the new century, then we see that the focus has been further shifted to improve the performance as well as the further reduction of the cost. Then in terms of power electronics, we focus on the packaging, the thermal management, the reliability issues, as well as the digital tools used in the design, control, and the monitoring of power converters. So in the past, that was about the explorations. Then we focused on the basic functions of power converters, and then today we focus on the further improvement of the performance of power electronics, because that's the major components in the energy conversion and the utilizations. And along with this development of power converters or power electronics, the power semiconductors in the past, then we use these mercury arc rectifiers, and then we have these uncontrollable devices, power semiconductor devices, then full controllable power devices, and today we have been using wide bandgap devices that brings higher efficiency and higher reliability. But of course, this is also depends on the design and the control of the power converters, even you are using wide bandgap devices. So that was the brief history of the power electronics development seen from the global perspective. And back to ZJU, Zhejiang University, the power electronics has also been developed fast in the past 50 years. And actually in 1972, Professor Wang, the academician of engineering, of Chinese engineering, has established the first programs in power electronics. Since then, we have power electronics programs in undergraduate programs and postgraduate programs and the PhD program as well. And actually, the power electronics, the scopes of power electronics, we consider it was defined by Dr. William E. Newell back to 1973. And actually, the programs established in China was 1 year before the definition of the scopes of power electronics. But anyway, what we are talking about power electronics, that's a multidisciplinary subject involving electronics, power, and control. And today we will discuss how we use power converters to condense the energy, electrical energy, and how we control such energy. And the research at Zhejiang University is quite broad. We have research activities on power semiconductor itself, on power modules and power supplies, as well as power converters in different applications. For example, in data centers, in transportation, electrification, renewables, of course, and other infrastructures in the country. And then that was the development of power electronics seen from the global perspective, and also the power electronics research and teaching at Zhejiang University. And then we will walk through how we can use power converters to condense wind and solar PV systems. So in terms of wind power generation systems, this slide basically shows the general structure of wind conversion systems. It can be broadly categorized into 3 stages. The first one is the generation. Of course, for wind turbine systems, we use wind generators, and then we have the conversion stage that based on the power converters, and then the grid side is of course the grid, and that's the load side still governed by synchronous generators. And for power converters, the standardized module or the most widely used power converters are 2-level converters as well as the 3-level converters. The standardized modules, they have been used in many applications. Then for wind grid-connected wind power conversion, there are mainly 2 concepts. The first one is based on this doubly fed induction generation concept. You can also call it as a parcel scale power electronics wind systems, because the wind power is partially processed by the power electronics converters. And such a concept is a state-of-the-art solution, and this has been used also in many commercial wind generation systems. And the other concept is called this full-scale power electronics-based wind generation systems. You can use a synchronous generator or asynchronous generators. Here, the power is fully processed by power electronics. And this concept is also the state-of-the-art solution and used in many commercial and practical projects. And it is also increasingly used in the wind generation systems, because its capability to fully process and control the wind energy from the turbine. And this concept can use gearbox or remove gearbox, depends on the applications. And for the power converters used in the 2 concepts, basically here shows the 2-level power converter topologies. As I mentioned, this is a standard solution. For example, the 2-level voltage source converter back-to-back solutions. This is a proven technology. Standard power devices and modules can be used, and the power electronics actually decoupled the power from the grid and the generator. But these 2-level solutions have some drawback. For example, high dV/dt, 2 levels. You have 2 levels of voltage output. Then you need to use bulky filters to make the output to be sinusoidal. And another thing is, for this solution, you need energy storage element at the DC link to sort of achieve the power decoupling between the generator and the grid side to sort of balance the energy flow. And another drawback for this solution is high power loss at high power applications, lower efficiency. And compared to this one, another 2-level power converter topology is based on diode rectifiers. You use diode rectifiers, then you have the boost stage to boost the voltage. Then you have this 2-level voltage source converter to connect to the grid. This is a low-cost solution suitable for permanent magnetic synchronous generator. And again, this also has a standard device and standard modules to easily assemble the entire systems. And this topology has some drawbacks. For example, low power quality on the generator side, because you are using diode rectifiers. That's uncontrollable devices. Low frequency torque position may be seen in the drivetrain. It is also challenging to design the boost converters if you have a higher power, and the device, how to select the device to withstand such high power is a challenging issue. And that was for more or less for low power applications in wind. And if you wanted to have solutions for higher power systems, then you can use either parallel the systems using different modules. And the other way is you using multi-winding generator. Then you have each winding, you have each a module to process the power. Then the total power processed by the entire systems can be much higher compared to a single module. So parallel is a solution to handle high power in wind turbine systems. Then another solution to handle higher power is to use multi-level converter topologies. For example, the 3-level NPC back-to-back converters. This is the most commercialized multi-level converters. And because you have more voltage levels compared to 2 levels, you can use small filters to get nice output at the grid side. And this can do higher voltage and larger power. And also it is possible to extend the power capacitors by paralleling more power converters. But it also has some drawbacks. For example, unequal losses on the power devices need to do the midpoint balancing in the operation. And other solutions, for example, you can use a 3-level H-bridge based back-to-back converters, and it achieves more equal loss distributions among the devices and among the modules. And it also has a redundancy. If 1 or 2 phases failed, then you can the system can still send power or process power. And it has higher controllability coming from the 0 sequence. And if you use these solutions, you have the possibility to utilize the 0 sequences then to achieve more advanced control. But it also has some drawbacks. For example, you have to use open winding for generator and transformers. The cost is higher. And another challenge is that it is difficult to extend its power capability because it is difficult to connect in parallel. And that was the solutions to achieve higher power using either parallel solution or you use multi-level technologies. But the other solutions can be the series connection. For example, as shown in this slide, you can connect the power modules or the power conversion modules in series. Then each phase can process higher power than the 3-phase systems can process a higher power. So this is another way to increase the power processing capability of wind power converters. Of course, one of the series connections you can see is the modular multi-level converters. You can use a half-bridge solution or full-bridge solutions to connect them in series as the phase, the capability of the phase can process higher voltage and higher power than the entire systems can handle higher power. Of course, if you use such wind turbine systems for practical applications, then there are tens or even close to 100 wind turbines in the entire wind park. So how you connect such a higher power systems? Basically, first you can use. Of course, it depends on the solutions. You can use DFIG, doubly fed induction generator based solutions, or you use this PMSG solutions. And if you have such higher power, typically those systems, wind parks are offshore wind turbine systems. Then you want to transfer this offshore energy to onshore systems. Then you use this HVDC technologies, high voltage DC transmission systems to achieve the connection or to achieve the electricity transmission. Yeah, that was about the power converter technologies for wind. And in terms of PV systems, there are also a couple of solutions or concepts of grid-connected PV systems, depending on the power level or voltage level. For example, for the modular converter systems. Typically, this is a single phase solution, a few or several hundred watts, and it is for small scale systems. And if you have a bit higher systems, you can either use DC technology. For example, you use DC-DC converters, then you connected the DC output to the common DC bus. Then you use a single DC to AC converter to connect to the AC grid. But this part is called a DC grid. And this can be a single phase or three phase connection, and it is for small scale or commercial systems. And for residential or commercial applications, typically we use either a string inverter or multi-string inverter, as shown on this slide. And then the typical power rating for such a system is several tens up to several tens kilowatt. And for further larger scale systems, commercial applications or grid applications, we use this central inverter technology. And you have a lot of panels connected in series and then in parallel to get higher power and high voltage. Then you use a single central inverters to connect to the grid. And the typical power rating for such systems is around several hundred kilowatts. Yeah, then that was the general concept for grid-connected PV systems, and in terms of power converters, and for micro or small-scale converters, and we can use microinverter or microconverter. For example, the DC optimizers based on conventional DC-DC converter or based on this flyback DC optimizers. And for microinverter, that's a single unit then directly connect converter panel level voltage or power to the level for the grid connection. And then for string converters, and the first one, of course, we can use this full bridge or H-bridge PV inverter technology as shown here. Here it is also called transformerless PV inverter, because we are not using transformer in this connection. But such systems have some drawbacks when you remove the transformer. For example, you will see leakage current in the systems, then you have to address this issue, and through topology innovations, or you modify the modulation strategies. And for this H-bridge based transformer-less inverters, the typical power level is a few or several kilowatts to several tens kilowatt, and this is the standardized solution. You can easily scale it up for higher power, but the efficiency is relatively low compared to other transformer-less solutions. For example, like this H5 inverter, the efficiency can be up to 98%. This Henrik inverter systems, the efficiency can be up to 97%. Actually, compared to the previous H-bridge inverters, those solutions add additional power devices like S5 in the H5 inverter and the S5 and S6 in the Henrik inverters. They achieve the isolation electronically, meaning that these will control those switches to achieve the isolation between the DC and the grid side. And for central inverters, this slide basically gives the general structure for central inverter PV systems. And actually for central inverter systems, the PV plant, there are more a couple of central inverters used in a PV power plant. This is actually seen as a parallel solution to handle higher power. For example, for large PV plants, for example, this 750 kilowatts by SMA, the rated power is over tens and even hundreds megawatts use many central inverters with power rating of up to 900 kilowatt. But for this central inverter solutions, typically the DC-DC converters are not used because it's difficult to design. And but in addition to the two-level converters, we can also use multi-level converters to achieve higher power processing in a PV plant. And furthermore, for the central inverter technology, you can use the series connection to handle high power. For example, on this slide, we saw this solid state transformer based 1500 VDC PV system, and each module is connected in series to handle the higher power, and it has a higher redundancy and higher modularity. But of course, it significantly increases component counts and the potential degradation, because you have a higher power exposed to the PV modules. Then you may have this potential induced degradation, and the topology may need to be redesigned to accommodate this higher DC voltage. Yeah, that was about the power electronics converters for wind and solar PV. And in terms of control, we have to achieve different goals at different stages. For example, at the generation side, we need to optimize the power because the energy production is relying on the ambient conditions. For example, for wind, that is the wind speed, and for PV, that depends on the solar irradiance level. So we have to optimize the power to extract as much energy from the generator side. And the conversion side, then we have to achieve a reliable and secure the power supply, and the efficiency, cost, volume are of concern. And the other thing is we also have to contribute to the grid by regulate the active and reactive power according to the grid demand. And in terms of fault handling, and the entire systems or the power converter has to ride through faults if there are temporary faults at the grid side. And another thing is it is more and more required in today's power electronics based system. It's a communication. Then through the communication, we can coordinate different units or plans and to achieve more power optimization or energy flow in the system. And then in the past, the general control of power converters is called a grid following, which means then the power generation unit is feeding power to the grid, and we assume that the grid is a stable voltage source, has a constant voltage amplitude and a constant frequency. But this is changing because we are putting more and more power electronics converters, that's static converter systems, compared to the rotating machine-based generation systems. Then the control is shifting from a grid forming to the grid forming mode, which means the power generation system based on renewables is becoming much more active in the power grid. So compared to the grid following control, the grid forming control is such a control that we make our renewable generation systems to be active power sources. It can provide a stable voltage reference to the loads, which means it can act as a constant voltage amplitude, a constant frequency source seen by other loads. Then there are a couple of grid forming control. For example, the droop control, the virtual synchronous generator control, the virtual oscillation control, or power synchronization control. But in conclusion, the grid forming control is a way to make the power converters have or emulate synchronous generators. Then we can use the knowledge we gained in the past years to design the entire system or to operate the entire system. So in terms of virtual energy storage control, in terms of grid connected PV control, we have developed this virtual energy storage control in PV systems. This is a way to contribute the grid stability and by regulate its active power according to the frequency deviations. And also we can contribute to the frequency change rate that is related to the inertia and the damping. So the basic concept is we regulate the PV system power operated at this such a line. Then this reserved energy can be released in order to support the frequency. And if you need more energy, or if there is an over frequency issue, then we can further reduce the power from the PV panels. Then this is the operation of storing energy. So it looks like a physical energy storage or a physical batteries. That's what we call it, virtual energy storage control, but there's no physical energy storage devices. Then we have done a simulation of PV systems. The power rating is 20 kilowatts. Then in response to a frequency drop, then how we can use this reserved energy to improve the frequency profile of the grid. And then for multi-level converter topologies, we give an example, this multi-level DAB converters. This is we see some applications in medium voltage DC systems, because when we use this multi-level dual active bridge converters, we can improve the efficiency, the reliability, and we can also achieve isolation and softer switching in such systems. That's why this is increasingly used in medium voltage DC system, as shown in this figure. We have PV panels, we have storage, and also auxiliary power supplies connected to the entire system. And for these multi-level DAB converters, we have to balance the capacitor voltage, because as I mentioned, then this can have some issues. The voltage unbalance on the capacitor, then it will increase the losses and brings additional side effects. Then we have to balance the voltage, and what we have done is using a complementary switching state to compensate the unbalance in order to achieve equal voltage across the two capacitors, as shown in this in experimental test results. And furthermore, we give an example for this impedance source converters. And why we have this impedance source converters, because for applications like microinverters, and we have to connect the low voltage PV panels to the high voltage grid. The PV panels typical voltage level is around several tens watts, but for the grid side, that's a few 111 volts or 220 volts. So this is it requires a very high boosting from the PV panel to the grid side. If you use traditional two-stage conversion systems, the efficiency is usually low. What you can do is to use this impedance source networks. It's passive based, then you can achieve higher boosting from the PV panels. Then you can connect it to the grid. But for such a system, we also have some issues to address. For example, the current ripples. If you minimize the ripples, you can use smaller inductors, and this can improve the switching and improve the efficiency. And there are a couple of solutions to achieve so, like increasing the switching frequency or using coupled inductors. But through the control, actually, we can achieve this target. We modify the modulation, and by utilizing the additional shoot-through states for the impedance source-based converters, then we achieve the ripple current reduction. And in terms of modulation to improve the performance of power converters, I further give an example, which is published on ePrime. And this energy efficiency enhancement in full-bridge PV inverters with advanced modulations. We demonstrated this different modulation strategies on full-bridge inverters and that transformers operations. We compare the different modulation strategies in terms of how they can achieve the power loss minimization or reduction. And here shows some examples, simulation results. Then if we have different modulation strategies, how the losses will be distributed among the power devices. For example, if you use bipolar modulation strategies, and if you use hybrid unipolar modulation strategies, and some of the power losses can be reduced and the total losses can be reduced, meaning that the power distribution among the devices can be reduced. So if you are interested, you can refer to this paper for more details. And yeah. And furthermore, as we are connecting more intermittent renewable to the grid, and the grid is really challenged because you have the fluctuating power from the wind turbines, from the PV panels, then this creating some challenging issues to the grid. And if we to address this issue, and we see more and more energy storage in the systems. So for energy storage systems, it can be standalone, or the energy storage systems can be integrated with other renewable resources. Here we saw an integration of PV and battery systems. We use this cascaded H-bridge technologies to achieve this solution. And then for such systems, we have also to achieve the control. The control is becoming much more complex, because you have to manage the power flow between different converters in order to achieve the control targets. And here we demonstrate then how we use a cascaded H-bridge based PV battery systems to achieve active power regulation, and then further to achieve the frequency regulations in PV systems. Yes, that was basically all the technical content I want to present in summary. And we see much more power electronics in the power grid, and it couples different energy vectors. And we will see this even further in the future. And this is of course driven by the reduction of the cost of renewable technologies. But the other thing is also we want to have secure and reliable power supplies. For example, this energy island with the Power-to-X technologies in Denmark, and we have different energy vectors or different energy sources in the entire energy systems. And another thing is we see that digitalization and intelligence is of significant importance in today's energy systems, and this brings opportunities. For example, how we achieve the monitoring and the diagnosis of the energy systems. But of course, it also creates challenges, for example, cybersecurity issues in the entire digitalized systems. This need more efforts to address. We have to develop advanced power converters, but of course, advanced control. So topologies and the control are important to address those issues. Yes, with that, I thank you all for your kind attention. And I just wanted to bring up another point, is that we are operating, we are organizing a special issue on power qualities in modern electrical grids on E-Prime. So if you are interested, you can also submit papers there. Yeah. Thank you so much. This is thanks a lot to my mentor, Professor Fred Blobia, and my former students and colleagues, and my students at the Zhejiang University and the lab I'm running, Pencil. Thanks a lot.
Thank you, Professor, for such interesting presentation. Now I would like to invite participants to ask questions. So from participants, we have one questions from Sia. So he or she is asking, could you give us some comments how new devices impact the different power electronics topologies you introduced? Will some of them become more popular in the future or disappear from the industry with the coming of the WVZ devices? Please answer.
Yeah, thanks a lot, Kosim. Thanks a lot for the question as well. And I would say that we will expect a much more wide bandgap devices in the industry and also in the practical applications, because this is moving faster. Of course, it depends on the cost of these wide bandgap devices. And if you have a massive production of wide bandgap devices, of course, the cost is reduced, then we will see further larger scale adoption of wide bandgap devices. And in terms of the use of wide bandgap devices, it brings some advantages. For example, it can operate in more higher power, more higher temperature or ambient temperature conditions, and with higher switching frequencies, then you can really squeeze your power converters. I mean, the volume is really small, then it will bring easy installations benefits, and the cost can further be reduced. When the cost further be reduced, you will have more productions, then the cost of further reduced. And I would say that we will have more wide bandgap devices used in industry and in our practical applications. But of course, there's always a double-edged sword, and if you have very high frequencies, we may face like EMI, EMC issues in the power converters, and also the design of the magnetics, the passives. For example, if you are switching your power devices at megahertz or a few hundred megahertz, then the design of the magnetics can be a challenge issue. I hope I have answered the questions properly.
Okay. Thank you. So the next question is, what do you think about the new research in the field of solar PV converters?
Yeah, I would say that in the application of solar PV, the research of power converter technologies, basically it divided into two areas. The first one is for low power applications. For example, for the building integrated PV systems, because you have a multi-facets building, then you put panels in different areas of the building, then you have to handle the partial seating issues in such applications. Then the power converter design for that specific applications is a challenge issues, and there are quite a lot of research in these areas. And another examples for these low power applications is, for example, the solar powered cars, electrical vehicles, the bags you using solar PV panels. Then this power electronics converter design has to handle regular unequal power solar irradiance conditions. So this is something you have to do. And for high power applications, then how you can scale up the power level. For example, you use 3-level converters, or you use different other modular converter technologies to achieve high power applications. This is another area. I think this is currently they are divided into the two areas, and in between this, and it is more standardized, and it is more matured technology.
Okay, thank you, Professor Yang. And dear participants, you have any question further?
I had a question. And thanks so much, Professor Yang, for such a great presentation. I just wanted to ask about, you mentioned that in that area there's a lot of research in PV converters. Where else do you see quite a lot of research happening in this area right now, or do you foresee more research happening?
In PV?
Yeah. Mm-hmm. You mentioned PV, there's a lot of research happening in that area. Did I get that right? I wondered where else you saw, where you thought there might be big focuses for going forward.
Yeah, in PV systems, the other thing is how we can develop this high efficiency solar cells, because that's one of the most important things, because we sort of capture the solar energy through the solar cells, and there are quite a lot of research on this what is called I can't recall the name. Another technology, but not based on silicon technologies. The another technologies using different materials to fabricate the solar cells, and there are quite a lot of research in that areas to improve the efficiency of solar cells, to improve the stability of solar cells, and this is one they are doing. But the other thing is I think this is something we have to consider, is the reuse of the solar panels, because as I presented in this slide, and the PV systems has been increased in the past 20 years or 10 years, and we see then the lifetime for a PV plant or a PV panel is around 20 to 25 years. So from 2025, we will see a lot of PV systems will be retired. So if we see such a big retirement of PV plants or PV panels, how we could reuse such PV panels, or we just threw them away, then we will have a huge waste of solar PV panels. And there are also some research on the reuse of PV panels, I think in EU, in the States as well, different technologies. Of course, the metal frames we can easily reuse, but what about the silicon cells, then how we can reuse them? And this is maybe something we will see in the future.
Thank you. That's really interesting. Thank you. I think we have one more question. Karen, thanks for your impressive presentation. For traditional topologies and control strategies, could you please comment the opportunities and challenges of archiving the balance between power density and reliability in electric vehicles? I think that's going to have to be our last question because of time.
Yeah, thanks a lot. Thanks a lot for the question. Of course, for traditional topologies, they are standardized, they are modular, they have high modularity. So that's why the traditional topologies are used in renewables as well as in electrical vehicles. But if you wanted to achieve the balance between the power density and the reliability, what you could do is to sort of have a better thermal management systems in the power converters. And of course, this is from the hardware design. And if you have a good thermal management systems, then you sort of have a faster heat dissipations. Then you can sort of reduce have a higher power density, and the reliability can be improved. So there is a balance between the design, of course. And this is seen from the hardware perspective. The other thing is you can also achieve this through the control, but of course this is also to manage the thermal flow in the systems. Then you control the temperature in the systems to sort of achieve a balance between power density and reliability. Of course, this is one of the solutions. The other way is you use these advanced devices like silicon carbide devices and the wide bandgap devices, you have a higher switching frequency, then you sort of have a higher power density, and the reliability can also be improved because such devices usually they are claimed to have having a higher reliability compared to the silicon-based devices.
Thank you, Professor. Thank you. Anyone? Thank you. Any further question?
I think we need to wrap up because of the time.
Yeah, we have time.
Do reach out. There's Professor Yang's email address there. Is if you would like. I hope that's okay if people contact you direct. Professor Yang.
Yeah, that's no problem. So if they have further questions, and we can discuss it through the email. Yeah.
Okay. Well, thank you so much for this evening, your evening, and taking the time to present this and prepare it for us. It's been really great and very much appreciated. So the slides will be shared after the presentation with everyone who's attended. And yes, thank you so much again. We'd like to invite your submissions to the journal as well. If do go to ePrime and have a look at those articles. But thank you everyone for joining us today, and do look out for the next webinar in the series. Thanks. Bye.
Thank you everyone. Bye bye.
Thank you. Thank you.